Hello, everyone. My name is Tilman Buchner. I'm Director of Engineering at BCG Digital Ventures in Berlin. And I have the pleasure to talk today about the future of automation and why we cannot wait for the cloud, or waiting for the cloud is not an option. Before we jump into the topic, let me explain to you, or let me discuss with you the difference between what is a complicated and a complex system. Because we think that it's of high importance if we talk about the future of automation that we can differentiate these two terms. So at first, what is complicated? A good example of a complicated process, for example, is flying an airplane. So if you would ask your friends, is it complicated to fly an airplane? Maybe most of them would answer, yes, it is. But if you would state the same question to a group of professional pilots, most of them would say, no, it's not complicated, because they have the sufficient experience and knowledge to fly such an airplane. So in a nutshell, you can handle a complicated system once you have the experience and knowledge. But if we think about a complex problem, and a complex problem might be, for example, the weather, or like here, a football game. A football game, you cannot predict an outcome. You can influence a complex system and you can oversee it, but you can never ever predict an outcome. And this is very of very importance if we think of production systems or machines. Because you can think of that each shop floor consists of complex and complicated processes. And everything which is complex, you cannot influence and you cannot predict. But everything which is complicated, you have a chance to control it with rules and receivings. So how did we deal with this in the past? So in the past, we applied the lean management approach. Lean management is a well-known phenomenon since decades. And what lean management tried to do is they tried to reduce complexity by redesigning processes. So what we see today is we try to reduce complexity in the real world and try to apply a rule-based automation approach to everything which is complicated. And at the end, the system of today's automation looks like this, what we see here on the left side. We call this rule-based automation. And rule-based automation works like this. We have input data and we have a mapping. The mapping consists of the rules about the system. And a computer or control system can compute or calculate the corresponding output. And as you see here in this pyramid picture, so a production system, so the real world, consists of complicated processes and complex processes. As mentioned before, we try to reduce complexity by lean management, but now we deal with the complicated processes. But the level of control of complicated processes is limited due to the fact that we cannot map all the possible situations of complicated processes within rules, because sometimes you don't know what might happen in future. I'll give you a concrete example. For example, if you want to program an AGV, automated guided vehicle, you try to come up with this rule-based automation approach and think of any arbitrary situation such an AGV could be faced with. And let's assume, for example, you could think of 100 different use cases. But in reality, the AGV might be faced with 101, the 101th use case, and needs, for example, to react if a person steps from the left to the right. This is something which you have forgotten at the very beginning when you try to model your system. And as a consequence is, you need to deal with production interruptions, because your AGV will stop movement and will turn into a failure mode. And this has a consequence, a negative consequence, of your overall equipment effectiveness, because you lose productivity. So now let's come to the future of automation. And the future of automation, we think that in future we will turn from a rule-based automation to a goal-based automation system by leveraging artificial intelligence or machine learning. So what's the difference? The difference is that system of the future has also input data, but also output data, and we leverage AI with calculating the corresponding mapping. And this is the big difference between the existing automation system, which we know from nowadays, and the future automation system. And as a consequence is that we can unlock this OAE uplift potential by applying AI and, as we will see later on, edge computing. So in a nutshell, AI and edge computing will have a huge impact on the overall optimization potential of the OEE. So now let's turn into a more technical discussion. This is the theoretical background, and as mentioned before, there are two new technologies available which helps to turn this idea or concept into reality. And this is edge and cloud computing on the one hand side and artificial intelligence on the other side. And what we see from an automation industry point of view is that there is a clear shift from the well-known automation pyramid, which we see here on the left side, which is a well-known architecture since decades. And nowadays, what we find in most companies is an architecture which we see here in the middle, which we labeled with today. So today, if we differentiate the IT and OT world, so the information technology, which is mostly seen at the management level, so everything which is related to ERP systems, customer relationship management, PLM systems, most of them leverage cloud services. The beauty of cloud services is that you can correlate data with external data sources, for example. And you can do this with ease because you can leverage standard protocols, standard interfaces, and so-called service-oriented architecture. You can orchestrate different kind of services and create a new value by connecting these dots. In the OT world, the operational technology, so everything which is taking place on the shop floor, the world today is a little bit different. For sure, maybe we don't have monolithic architectures today, so also here it turns into a more modularized control architecture, and we see a clear trend to a unified communication protocols like UPC-UA, but it's still not as easy as it is in the IT world to gather data, to correlate data, and to leverage data and gather data while running and using this data for optimization. This is a big difference. For example, if you compare a shop floor, a production system today, with a self-driving car. A self-driving car leverages data, gathers data, and uses this data during runtime for optimization. But today you don't see something like this in a production environment. And the reason why is because it's so hard to exchange data between the IT and the OT world. So this is a well-known phenomenon of there is a gap between the IT world and the OT world. Now, in the near future, as mentioned before, when we introduce edge computing, then we can apply the beauty of a service-oriented architecture, or the idea of a service-oriented architecture from the IT world, we can apply this to the OT world. And this opens up a new window of opportunities for two things. We can generate savings on the one hand side, because we can increase productivity, enhance quality, and improve also the availability of resources. But we can also leverage edge computing and the over-the-top AI services by generating new opportunities of growth and new services. So, as mentioned before, the big difference between these two systems, for example, in comparison with a self-driving car with an automation pyramid today, is that it's not only about gathering data, it's about gathering data, capturing data, and using this data for learning and optimization. And to enable this, you need a new kind of architecture. And you can think of this that existing production system can be enriched with so-called edge computing functionality. And in general, there is a three-step process. So you can think of establishing connectivity to the physical world or to existing industrial PLC. Start sensing. Sensing means that you're able not only to send all the data to the cloud, but just friction of the data. So we talk about pre-processing of data. Second is that you can infer, which means you can, once you upload the data to the cloud, you can leverage machine learning capabilities and unlock machine learning capabilities of the cloud for the shop floor. And last but not least, edge computing technology gives you the ability to establish a bidirectional communication, which means we're coming from a time where we talk about internet gateway devices, which only offers a one-way communication. So you can gather data, pre-process data, maybe send data to the cloud, but there's no opportunity with an internet gateway device that once you infer something and come up with an insight and optimization, that this can have immediate effect on the production. But edge devices in correlation or interconnection with cloud services gives you the ability of a bidirectional communication. So once you generate an insight in the cloud, this can have immediate effect on the shop floor. And this gives you the ability that you can gather data, you can interpret your data, and use this data for learning and optimization on the fly. So in a nutshell, in future, we think that the automation pyramid will turn into a new architecture layer model. And this model consists of 5 layers. At first, it's all about the control and field level. You can think of any arbitrary mechatronic system. Either it's an actor or a sensor. And at the very beginning, you need to establish connectivity to these actors and sensors. And this is all about the actual edge device. Within the edge device, you can differentiate between hardware and software. So an edge device for sure consists of hardware. And then an edge device could be anything from a single board computer, like a Raspberry Pi, which is very cheap in comparison to industrial controller, maybe around about $30, to more sophisticated, more powerful devices, which you see or find, for example, from companies like Qualcomm or Intel. Then what an edge device needs to do is it needs to establish a connectivity, so it needs to have physical interfaces. If we talk about industrial devices, you also need to support different kind of automation protocols, as you see here at the upper left corner. What we see here is a trend to a unified protocol. Maybe in future it will be UPC UA, maybe MQTT as a well-known protocol for the communication between the edge device and IoT cloud will win this race. This is something which we will see in future. Then another important aspect is the actual edge device operating system. Amazon, for example, in the Amazon world, it's called the AWS Greengrass operating system, which is, let's say, the heart of the actual edge device. And the edge operating system is responsible for doing the data pre-processing, for managing if you have an intermittent connectivity, and also to synchronize data between the IoT cloud and the actual edge device. And also ensures security, so ensures a secure connection between the IoT cloud and the actual edge device. And then the edge hardware is also fitted with different kind of communication modules to support different kind of mobile networks, reaching from NFC to Zigbee to GSM modules, so to be able to communicate with external network infrastructure. Let's go back to this diagram. So once you took a decision on what kind of hardware you need to establish a connectivity to the field level, and you installed your edge operating system, then you can start engineering your actual edge device. And the edge device has one ability, which is to execute code locally, which means the edge device, and this is where the term edge comes from. So we shift computational power and storage and logic from the cloud to the edges of the network. Once you gather data and you pre-process data, you send this data via MQTT to the actual IoT cloud. And once the data in the IoT cloud has been uploaded, the next step you need to do is you need to build up your data processing pipeline. And this is also a very important point, because if you don't build up your data processing pipeline, once your data are in the IoT cloud, the data would be disappearing. So it's of highly importance to build up this data processing pipeline. So what is the actual challenge on the data processing pipeline point of view? If we talk about data, then we need to understand that data is coming in different sizes, velocities, and forms. So you can think of, if we gather data from a field device, then we maybe talk about a data stream. So it's more an event-driven data handling. If we other forms of data might be, for example, medias or log files, and in general, these types of data are stored in an object store. Or if we talk about data which has been generated by human beings for applications, these are, in most cases, transactional data, and you can differentiate between SQL and non-SQL databases. So within the intelligence layer, the first thing before we can think about applying AI or machine learning algorithms, it's about building up this data processing pipeline and to making sure that we have a dedicated data processing pipeline for each kind of data we need to deal with. And it's of highly importance because the complete pipeline and the way how we engineer the pipeline has a huge impact on the latency. Because here data is coming into the system, and we need to define what kind of technology needs to handle this data. And after storing the data, we can apply an ETL process and start thinking of how to analyze the data and how to generate insights out of this data. And last but not least, it's about sending an answer to the system. So let's go back to this slide. So the idea is we establish connectivity. Here too, we apply our edge device, we pre-process data, we send data to the IoT cloud, then we pump this data into our data lake because we establish a data processing pipeline. We can also correlate data with external data. And once we build up our data lake, we can start thinking of to apply machine learning capabilities, think of all the beauty of machine learning capabilities, supervised, unsupervised learning, deep neural networks. Depending on the use case which we need to solve, we pick the right machine learning algorithm. And once we generated the insight, we can build up our business logic and leverage a concept which we call also the digital product shadow, which gives the ability to send or to apply the insight directly back to the actual edge device. So technically speaking, for example, we can deploy Lambda functions in the AWS world to the actual edge device, and here we can take immediately effect on the insights which we generated here in the intelligence layer. And for sure, you can also think to generate on top of this user interfaces, and here you have a huge bandwidth of opportunities reaching from creating mobile devices, web applications, or also augmented reality applications, or leverage new kind of devices like an Amazon Dash Button or Amazon Alexa to control your system or to interface with the system. Okay, let me give you a concrete example of the automotive glazing industry, how you can leverage AI and edge computing technologies to improve the overall equipment effectiveness of a process. We built a physical demonstrator showcasing the potential together with a laboratory for machine tools and production engineering at Aachen Technical University, KUKA, the robot manufacturer, and AWS. So what is the actual problem of the automotive glazing industry? And I think it's beyond the automotive glazing industry because most production companies are faced or need to deal with process disturbances. And process disturbances can affect, for example, production interruptions, which have a negative impact on OEE. So in particular, for the automotive glazing industry, think of if you produce glass, you can only produce glass within tolerances. This is because of the Tilman effect, which you leverage when you produce glass. So you use an oven to produce glass, and the oven thing of the very beginning of our talk, is a complex process. So you cannot predict the outcome of this process. And as a consequence, every glass is a little bit different. And different means has a different geometric shape. It's okay from if you think of, you can produce within tolerances, but the problem is that if you want to handle glass, that each robot within the production line would expect that each windshield has the exactly same three-dimensional shape, because the robots handle each workpiece so accurate. The problem is that in reality, you need to deal with production interruptions because you need to reteach your robots a couple of times per day because of these variances within your oven process or the process of producing glass. And we thought about how to solve this problem. So how to redesign the complex process on the one hand side, but also to enable a self-optimizing control process to prevent production interruptions. So how did we done this? We set up a demonstrator which consists of 4 working stations. The first working station is a so-called cleaning station. The idea of the cleaning station is that once the glass comes out of the oven, it needs to be cleaned. And for this, we use the smart robot, KUKA robot. It's a collaborative robot. And the benefit of this collaborative robot is that while cleaning the windshield, you can actually measure the 3D shape of this individual windshield. And then we came up with the idea that we use this data while cleaning the windshield to store it in a so-called digital product shadow. So the digital product shadow is the actual digital representation of the physical windshield. And then we attach this digital product shadow to the actual physical windshield. And when the physical workpiece is moving along the production system, the digital product shadow is attached to this individual physical workpiece. So back to our example, after the cleaning process, there is a primer station. And the primer station is about putting a primer line on this windshield. And now you can think of what happens. This primer station, the robot of the primer station, is also fitted with an edge device. So at first, it identifies these individual physical glass and accesses the digital product shadow of this glass. Then downloads the 3D model of this individual glass, which is the outcome of the previous cleaning process. And we use the edge device and the computational power of this edge device to generate the needed primer line on the fly out of the 3D model of the windshield. And everything is taking place in milliseconds. And the beauty is that you can call this system a self-optimizing robot handling system, because we moved from a dedicated, rigid control architecture where each robot executes every time the same logic to a system which can adapt itself, because it leverages the digital product shadow, accesses this, and generates the needed robot paths, the individual robot paths on the fly. And this gives a new degree of freedom and a new degree of optimization, which has a positive impact on the overall equipment effectiveness. And at the end, after the primer station, we use image recognition technology to inspect the quality of the primer line. So we use some kind of edge detection and machine learning capabilities to see if we put the right amount of primer on the windshield and if the actual primer pass was accurate. And this is also a kind of control loop, because we can improve the system over time. So let me show you how this looks like in reality. I would like to share with you a short short video. Here's some screenshots from the actual physical demonstrator. So you see the primer station, you see the previous cleaning station with a collaborative robot from KUKA, and here you see what's happened behind the scene when we do the actual edge detection and applying a convolutional neural network here for coming up with a likelihood, how confident we are that this is a positive primer line, yes or no. And here at the right corner, you see an iPad application which leverages all the REST APIs which we make available in the cloud, so we could develop with ease and very fast a user interface on top of it, which showcases the individual working steps, showing the interconnection between the actual edge devices and our cloud services, and also see how we can train and learn our convolutional network in the cloud, and then leverage new machine learning capabilities, AWS intelligence services to apply the actual algorithm to the edge device and execute the image recognition technology on the edge device. Also, a short video which gives you an idea of that everything also moves, so it's not theory. Hold on, let me start the video. I hope you can see it. So we moved the actual windshield out of our storage to the cleaning station. The KUKA EVA robot cleans the windshield, and while cleaning, he's measuring the 3D shape. He stores the data in the digital product channel. This is everything happens behind the scene. This is the primer robot who already accessed the digital product channel and derived the needed robot path on the fly. And then last but not least, we hand this over to a quality inspection station where we use image recognition technology to inspect the actual primer line. You can think of, if you want to do this in a more, let's say, professional way. So at the very beginning, we started with an MVP approach. So we used Raspberry Pis, very cheap thing about computers, to build up the entire topology of this architecture. You can think of in a future scenario that will replace Raspberry Pis by industrial-ready QuickBooks PIs. You can also think of, we used remote service interfaces with KUKA robots. Maybe if we want in the next scenario not only connect to a KUKA robot but to any other arbitrary machine tool, you can think of this might be, for example, a backup industrial PC fitted with a code assist control, and we can establish a connectivity with UPC UA between the edge device and the industrial controller. And the communication between the edge device and the IoT cloud is taking place via MQTT, as you see here. And the actual bidirectional communication, which we mentioned at the very beginning, this is what you see here, because we can not only send MQTT data from the edge device to the IoT cloud, we can, once the data has been arrived in the cloud and this then be processed by our data processing pipeline, and we generated insights, then we can put these insights into a new Lambda function and deploy this Lambda function so that our insights can take immediate effect on the actual edge device. This is one way of communication. The other way is that with this new AWS intelligence services, you can also deploy machine learning algorithms from the cloud to the actual edge device. So this is a very powerful and impactful control functionalities, which turns an internet gateway device into a real edge device, because you can do a bidirectional communication and you can benefit from the power and the optimization of the cloud immediately on the shop floor. Okay, last but not least, in a nutshell, so you've seen and get a first idea of what a digital product channel concept looks like. So the digital product channel in a nutshell is that in production system nowadays, you try to put all the intelligence to the machine. So the machine is smart. You handle, let's say, dumb workpiece. We inverted this concept and thought about that we built up digital representation of the actual workpiece and enrich this workpiece with digital product shadow over time, and make this information available for each working station which needs to deal with this workpiece. So it's an inverse approach of existing control architecture. We established connectivity with edge devices. We applied a convolutional neural network for the quality inspection. We are able to control in more or less real time. So real time is a broad definition, but real time for us means that we could control these robot handling processes in more or less 4 microseconds. This was our definition by real time. And we leverage the out-of-the-box security features of AWS, so to making sure that there's a secure connection from the actual shop floor to an outside cloud infrastructure, in this case, the infrastructure of AWS. What you see here was an example of the discrete manufacturing industry, but for sure you can think of that you apply the general logic also across industry to other use cases, reaching from mining, construction, energy, agriculture. I think there are a lot of opportunities inside and outside the shop floor where you can leverage this kind of new technology. And it's not only the technology. What I would like to bring over in this presentation is that the future of automation is that we turn from a rule-based automation approach to a goal-based automation approach. And this means that we can unlock OEE potential within the complicated processes within your production. Because, as we mentioned at the very beginning, everything which is complex, we can just influence and monitor, but we cannot predict any outcome. So let's focus on everything which is complicated. But if you want to unlock the full potential of the control level of complicated processes, think of how you could leverage edge computing and AI technology to turn from a rule-based approach to a goal-based automation approach. Last but not least, I think at the end of this talk you will see a chat window, so feel free if you have any questions, please post it into this chat window, and I'm more than happy to answer your questions. Or if you have the chance and you are around Hall 6 at the Hannover Fair on the 23rd to 27th of April, we are more than happy to welcome you at the AWS Digital Factory, BCG Digital Ventures, and the Laboratory for Machine Tools and Production Engineering will showcase the automotive glazing industry demonstrator, which we've seen before, in reality at the Digital Factory, and we are more than happy to discuss with you the future of automation. Thank you.